Good evening, everyone. Hope you are doing well. We are going to learn how to do heteroscedasticity or homoscedasticity test with Python software. We have already made kind of videos showing how to download software Python and the interpreter. Make sure that you have already watched those videos. Then here to remind you that Python as other softwares can help us to execute or run our models and also statistical econometrical tests. And it can also help us to do what we are calling programming, pure programming and so on. And what is interesting with Python is it's giving result in details. Okay, what we will be doing is what you can see from my screen, but I want to show you how Python is presenting result. It's giving the name of the model, the time you are just running the model. Now those R square, F statistics, and so on are given also by other software that like AIC, BIC is not or were not cannot be given by other software from our statistical software. And here also you can see we have additional information about the distribution of data, like we have for free the analysis of normally tests or this normal distributions. For example, we have Jacobera and the result, we have skewness, kurtosis, and so on. That's the point. Then it's better to also, interested to know how those tests or those models are run in Python. And here, the purpose or the objective is to run a heteroscedasticity test. But before to do that, we need to take our data. We need also to run the model and so on. That's what we'll be doing around here and so on. Okay, let us now do. We can create another file, or we can just delete whatever is here and start from the beginning. You will see what is happening. Okay, then from here, Python is also working like R, where you need to install some kind of package, or you need to load the packages. Here they are called modules and so on, but the same processes and so on. The point here, we will be in need of some kind of modules. The first one is pandas. We will import pandas, import pandas as PD. Okay, that's the first one, which will help us to import our data here. And after it, we will need of import stats model. Yeah, stats model. Okay, or stats model API as SM. Okay, we will also need this test, this heteroscedasticity test we want to use, import, or we can say from. Okay, let us run what we have here for first, and now come to import this one. Okay, whenever you run and you have process finish with exit code, meaning that whatever you did was correct, is okay. Then from stats model, stats, okay. Yeah, you know that heteroscedasticity test is a diagnostic test. Then we need from here, we'll import it. From this one, import. Okay, we have many kind of heteroscedasticity tests like white test, brush pattern test, golf test, and so on. That we will be using here brush pattern. Those one which are used mostly are brush pattern test and the white test, but we will take brush pattern test. brush pattern, and you will see as it, for example. And let us execute. Here is Shift F10, or maybe you can just go there and click it, will run also. Yeah. Then up to now it's okay. Then let us talk about heteroscedasticity, homoscedasticity. What is this? Homoscedasticity test is what we are, it's just a post test after running a kind of model. I want to check if our data uh, is the variance of the data is equal, or uh, it is unequal. For example, homoscedasticity, the meaning of homoscedasticity is like the variances of all variables are the same, okay, or the variances of the residuals of your data is the same. Meaning that how the variance are, the spreadness is the same from the mean. Yeah, that's one is what we need from our data before to rely on the prediction we will be doing. Now, when it says homoscedastic, there is no problem, we can proceed. But when we run a model and we check on homoscedasticity and we realize that we have heteroscedasticity problem, we need to correct some kind of things before to proceed, because our results will be biased. We cannot rely at the end on the result and so on. That is for this reason it's called diagnostic test. To see if everything is okay before to rely on the model, the result of the model. That's the point there. Then let us proceed. Now let's say we need now whatever we are doing around here, we need to import our data, or the data we want to use, for example. Then we will call it data. As you will see that we will use pandas as PD, which will help us now to import our data. The data I want to import here is in CSV format. If yours is on Excel format, you can use read Excel, then CSV, read CSV, and from there, I can now go and take my data. I should know where my data is, which kind of data I want to use, and I will go at that place. And now, can you see here, I want to take which one, which is in CSV format. I can click on it and right click. From right click, properties, and now I can copy the location of my data. It's very important, I need it. And now, after the importation, I should remember the name of the data, which is which one, and go in there. For example, now I can paste it. And this one, I have now to write the name, which one, and add CSV. That's from, if your data is in Excel, can you see that you have to add the XLS, it's not CSV. Then this command, for example, will allow me, or will help me to import my data around here. By the way, if you have not subscribed to our channel, you can subscribe, please. It will allow us to learn a lot of things together. Yeah, then I have already my data there, but I need to view them. I need to see them. Then print, and I want to see just the first 5 lines, rows of my data. Now I will use a head, for example, head, like the way it is. Now let's us execute, and now we can have 5 rows from our data. Can you see this data is just around? We have 1, 2, 3, 4, 5 rows, and this one will help me to see which kind of data I have. Are they quantitatives, binaries, or qualitative? That's the purpose when we are just printing our data, to see how they look like. Okay, you can go ahead also to see, for example, how our data is, well, are they integers or are they characters and so on. For that purpose, we can use also data info. Okay, okay, and you can see what is happening. It's telling me, for example, I have integers, I have float. Float here is like decimal or counting on so on. Now I see that I have those kind of what's my data look like. If I want also to describe my data to see the mean, minimum, maximum, and so on of all my data, I can use also describe and show it before to proceed data. For example, here, then I will use describe. Now describe from here, and now I can now execute. Then from there, you can see now all variables and now their means. Can you see their count here is just giving us the number of observations, the standard deviation, minimum, the quartiles, and so on. Okay, let's say that we suppose or we are suspecting missing values there, and you want to drop them in case they are around, you want to drop them. Then we'll say data equal data drop NA, and now I'm just doing that to drop in case they are around, to drop all missing values. And now, okay, they are okay. It's okay now. Since we are at this stage now, let's now define those variables which will enter in our model. First of all, okay, let's call them definitions, definition of variables. Okay, then first of all, let's say that's our dependent variable. We have to choose our dependent variables. Okay, let's say here, we want to run a linear regression model, then our dependent variable around here should be quantitative data or continuous one. We can take which, as you can see the structure, which can be a good one for our dependent variables. Then we will just write the which. And now we need also to define our independent variables. But the independent variables around here, they can be many. Then we can take now educations. First of all, we can take education. And after education, we can take experience also. After experience, we can take also, which one again? This one. And deep. Okay. Then we are defining again our independent variables around here. Okay, that's okay again. Then we need also to add a constant to our independent variable. If we did not, or we don't add a constant to our independent variables, at the end we'll get result without constant. Then we need to do that one with this SM add constant. Add the constant on X. Okay, that's okay now. And we can run. Then now we define our independent variable and so on. We can now regressions. Yeah. And from there, let's say we will call it model, which will be SM. Here we want to just to run OLS. Then the attribute of SM, we can see there OLS. Then after OLS, we need to say that Y is our dependent variable and X is our independent variable, and we need the fit of it. Okay, that's the point. Now we can run again. Okay. Okay, we have just run. Let us now say that we want to see our, okay, call the result model. Okay, then equal model, because the model is there. And now summary, we need summary before to see what is happening really, what we run and so on. Then execute again, that's okay. Okay, there is something when it's coming just like that, they are saying line 15, meaning that there are something I did wrong on line 15, really, because when I was writing summary, I added Z, which is not part of it. Then we can run again. Okay, we will see. Whenever you will see process finish with exit code 0, mean that everything was just okay. Then let's now see the result. Before to see it, we need to print what we did. Result model. Okay, then printing result model, we will see our result. Yeah, and it will come like the way I was showing you it before. Okay, we have our result here and we have everything. The name of the model, the method is least square. The data, I'm just doing it. And now the R square, which can allow us to talk about the fitting. Here is above 50%. We can say that our model fit well our data, or we can see the variability of the dependent variable is explained, or the independent variables are explaining at 63.20% the variability of the dependent variable. Okay, then I repeat again, I'm saying when it's above 50%, we can say that our model fit the data. That's one point, that's the conclusion. And the interpretation with this value is, we can say that our independent variables are explaining, or our independent variables do explain at 63.20% the variability of the dependent variable. That's okay. And now statistics is talking about all variables put together can be better, or can be better than the intercept model or not. Okay, here as you can see, the p-value, for example, is less than 5%, meaning that when we are taking all variables together, they are better than intercept model, for example. That's the meaning of it. And now, as I was saying, here we have additional information apart the result itself. We have now here those information talking about the normal distribution. Skewness is just allowing us to talk about the symmetry, if the data is symmetrical distributed or not. And the kurtosis is talking about the tail. Okay, for skewness, for example, when you have the value which is between minus 0.5 and 0.5, you can see that your data is fairly symmetrical. But when it is between -1 and -0.5, or between 1 and 0.5, you will see that it's moderately skewed, which is not, the meaning of it is saying that it's not symmetrical distributed. And now kurtosis, now the value of the kurtosis is like when it is greater than 3 or less than -3, there we will say that we have highly tailed. It's talking about the tail. It is giving us information about the tail of the data. Okay, when you try to plot this bell shape, we have now when it is greater than 3. In our case here, for example, we have the big tailed around. And the Jacobera test is one of the tests of normal distribution. As the name, here, for example, for those normal distribution tests, the H notes or the null hypothesis is saying we have normal distribution. Then it depends on what is the value of p-value to reject or accept this one. Around here, as you can see, the value of the p-value or the probability is greater than 5%, and we fail to reject the H notes and conclude that the data here we are using is normal distributed. That's the point. Just this one on bracket to explain what is happening around. Then our purpose here is to get to do normally heteroscedasticity test or homoscedasticity test. Then now, since we have the result, now we can proceed and do that. Now, I can just say homo test. I can call it a homo test. Okay, let's say heteroscedasticity test. Okay, then here we can call it a height test. Okay, the command is already we can call it home test. Okay, then this one we have already even imported it as it. Now here we need to put our model, the resid, And after it, model, and the exec. Okay, we can now execute. Okay. Now the point is, whatever you are just doing around here, to see it, you will need to print. Then let us print the result of this one. Oh, yes. Okay. We have it. The values are just around. But here, for example, can we see? We have 4 values. The first one is the coefficient of the heteroscedasticity test, or the statistic of heteroscedasticity test. And here we have the second level, we have the p-value of this test. What is interesting as is those two, but here is F and the p-value of the F, for example. Then here, the H note, or the null hypothesis, saying that there is homoscedasticity. Then now we have to look at the p-value to decide if we can reject or we have to accept it. Then the rule is, when it is less than 5%, we are rejecting the H note. When it is greater than 5%, which is 0.05, we are accepting, or we fail to reject H note. In our case here, the coefficient is 4.95, and now the p-value is 0.17, which is greater than 5%. And then we fail to reject. We fail to reject the H note and conclude that there is a homoscedasticity. But we can do better with our results. This one, the way that it is coming, is a bit confusing. We can make it prettier. Then we can call the first one coefficient homo, and the p-value p1. The second one we can say coefficient f, call it coefficient f. The second p2, second one p2. Okay, then and you will say, print me those one, saying that I want you to print this. I'm talking to the software. I want you to print this one, but I want you to print it in with 3 decimal points. Okay, and after it, I want you also to print me p1, that's also with 3 decimal points. Yeah, and I want you also to print me also the coefficients of f. And also with 3 decimal point. And I want you also to print me p2, also 3 decimal points. Yeah, and now until not everything online, and now again until finish with this one. Okay, then I don't want even to call it this one to allow me to have it in a good way. And since I know that there are 3 values which will come, I can just align them like this after the test, and now use this one, which can allow me now to get them properly, and you can see what will happen when I will run. Okay, they are telling there is something there which is wrong. Name is not defined. Did you mean hcof? Yeah. Okay. Everything which is above should be down also. No. Yes. I was having additional H there. Okay. Okay, we have it now. Okay, you can see the coefficients of the test. We are just doing heteroscedasticity test, and now the p-value, which is greater than 5% of F coefficient, we have P2 here. That is the point, is where we are going, and we reach now. Yeah. If you have not yet subscribed to our channel, please subscribe. We have a lot of to to do with those softwares and so on. This one is a heteroscedasticity test. We will be talking about normality test. Okay. We'll be also talking about t-test and so on in Python here. Yeah, thank you so much. Hope that this video will help you.